A machine learning model is trained in a massive cloud environment, heavily optimized and flashed to an edge device. But the moment it leaves that laboratory, it suffers from a frozen brain. It stops learning. The physical environment around that sensor does not stay static. A microscopic scratch on the camera lens or a seasonal shift in lighting steadily degrades the model's accuracy over time. That leaves you with two difficult choices. Relying on cloud APIs to retrain the model is slow and expensive, but attempting to run classical training directly on a 1 GB edge device guarantees thermal throttling or an immediate crash. The Welvet 1.0.3 engine offers a way out. It operates on a deterministic neural virtual machine and includes a matrix of 29 different training modes specifically designed to bypass those hardware limits. To get continuous on-device intelligence, you have to map the exact training mode to your specific sensor data. We are going to sort through that matrix and find the exact topologies you need. This diagram shows the Lucy score, the baseline metric for edge learning. It multiplies throughput, availability, and accuracy. Maintaining that middle metric, availability, or the continuous duty cycle, is the most difficult hurdle. Edge devices struggle to ingest live inference feeds while simultaneously running heavy training calculations. To keep availability high on constrained hardware, classical backpropagation is no longer the standard. The math has to change. Succeeding with Welvet on the edge requires shifting away from standard gradient descent and relying instead on discrete integer bit flips and target propagation. When standard stochastic gradient descent executes on a 1 GB device, it forces global execution thread locks and demands a massive activation cache just to calculate exact mathematical gradients. Those thread locks choke the system. Availability drops below 15%, meaning the device stalls and misses the live inference feed. This split-screen matrix compares heavy backpropagation locks against target propagation, which Welvet labels tween. Tween eliminates exact gradients, calculating a localized error gap instead. It applies a discrete heavy and bit flip directly to deeply quantized integer storage. This introduces a paradox with the learning rate. In traditional deep learning, setting the learning rate too high causes mathematical overflow. But in Welvet's tween configurations, a high learning rate is mandatory, ensuring discrete integer weights instantly flip states based on the error gap without overflowing. Real-time edge adaptation only works when you pair highly quantized formats, like 4-bit integers, with an aggressively high learning rate. Let's look at how this applies to specific hardware streams. A CAM1 profile handles high-resolution spatial data, typically used for frame-by-frame static visual classification. This graph plots accuracy versus learning rate for CAM1. Classical backpropagation fails, while tween split-head proxy async remains stable at peak rates. By offloading target generation to a secondary thread, the primary thread handles live inference. This pushes availability to near 100%. For these spatial environments, you should pair this async approach with a sparse configuration, noted in the engine as mesh tween split sparse. Sparse mode applies a dynamic error gap threshold. It actively blocks any weight modifications unless the incoming visual data has statistically drifted from the static background. Bypassing millions of redundant memory writes for unchanging backgrounds preserves the physical flash memory of the edge hardware and keeps the thermal load manageable. A CAM3 data stream requires a different execution stack. It handles high frame rate temporal reasoning to maintain continuous sequential tracking across time. If you attempt to run classical backpropagation through time across a sequence of CAM3 frames, caching all those intermediate temporal activations guarantees an out-of-memory crash on a 1 GB pie. The step-tween temporal modes solve this. They calculate target vectors for the recurrent layers at exactly the current clock cycle. Because historical activations are discarded the moment the target is generated, the VRAM footprint stabilizes into a constant time operation. But high frame rate temporal streams are incredibly noisy. A lighting glitch can generate immediate bit flips, causing erratic targeting that throws off the tracking system. The countermeasure for this noise is a specific mode called step-tween split linear cache. This configuration utilizes fast linear affine approximations and pairs them directly with stable momentum smoothing. The momentum smoothing mathematically dampens those erratic targets. When the camera feed glitches, the cache ensures the system doesn't immediately unlearn historical track graphs. For sequential streams, you have to trade mathematically perfect instantaneous reaction time for a stabilized model that survives noisy camera feeds without memory exhaustion. The Welvet testing suites show that within the 1 GB RAM limit of most edge sensors, the memory demands of classical backpropagation make it impossible to train without crashing the live feed. This flowchart maps out the required topology based on your primary sensor data type, splitting into spatial feeds for Cam 1 and temporal tracking for Cam 3. If you are processing static, spatial frames, route directly to the mesh-tween sparse mode. That path provides spatial adaptation while minimizing physical VRAM writes. It requires a high learning rate configuration to execute those localized bit flips. If your deployment relies on temporal tracking streams, route to step-tween split linear cache and the asynchronous head proxy modes. That temporal path replaces exact gradients with reflex approximations. It protects recurrent memory against high-frequency noise. Deeply quantized integer formats provide the discrete state changes needed for localized target propagation. These bit flips allow a sensor to adapt in real time, making sovereign continuous intelligence possible on standard edge hardware.